No, again, no. Okay. Boop. Hello, hello. Hello, yes. How are you guys? Week 5, and just a quick reminder that the assignment deadline is today. So I assume you all already finished or are about to finish and submit your assignment. Please also remember that you need to have discussions or a discussion session with your tutors. I also assume, because we have been talking with them about it, that you already discussed with each of them in your tutorial what is going to be the approach and possibly the time. If you are not aware, remember that there is a link on top, assignment in the second row, the second last, assignment 1 bookings. So if you click there, you should be able to see your tutor, the different times or availability from each of them. So that's going to be the time that you're going to be using, you're going to use to have their discussions. Remember that it's your responsibility to make all the arrangement. So if in case of whatever special circumstance, please contact your tutor, okay? It's not your tutor responsibility to contact you to have the discussion, but rather in the other way around, okay? All submissions need to be discussed. If you don't have the discussions, therefore, well, in that case, the grade or the mark is going to be 0, okay? Regardless, your code is working perfectly. You need to have the discussion, okay? Good. Today's topic is reinforcement learning. Well, we discussed last week about neural network, no? So we start, we're going to say from last week, going into more like machine learning approach, no? So we talked there that there are these 2 possible learning approach, like supervised learning and unsupervised learning, no? In which you may have the data with examples to train a model, or input-output samples. Or sometimes you have only inputs that you want to classify or build a cluster to, or maybe to analyze how similar they can be. But there is also a third approach, which is called reinforcement learning, in which you don't have the data previously, so you need to look for the data. You need to collect the data by interacting with the system, okay? Or, sorry, not with the system, interacting with the environment, okay? So that's what we are going to be reviewing today. Well, certainly this for me is one of the most interesting topic or lecture during the term for a couple of reasons. One reason is that this was my main research area during my PhD, and it still is my main research area. It's what mostly my group does. So we have many people working in different aspects of reinforcement learning. And additionally, I think I mentioned before, but we do not have a course of reinforcement learning yet. Therefore, for me, it's important to cover this aspect here in this lecture, in the AI lecture. And similarly, it's important for me that you can put your hands on it. Therefore, I can tell you from now that the second assignment, it's going to be about reinforcement learning, okay? So you need to try to, well, put attention, or maybe ask the question if you have questions, and so on. Okay. Yeah, let's move on. So this is what we are going to be talking today. I'm going to move this a bit on here. So a quick introduction. We are going to see the four elements of reinforcement learning. We are going to discuss about this exploration-based exploitation dilemma. We are going to formalize the agent-environment interface in which the reinforcement learning agent can work. Going to talk about value functions, and then at the end about temporal difference prediction, and a bit about other approaches which are it's not in the overview, but it's going to be included at the end. Okay, so let's start with the introduction. So let's have a look to this video first.
Pigeons are at either end of a small ping pong table. One pigeon pecks the ball as it comes toward him and knocks it toward the other pigeon. Other pigeon pecks the ball back across the table. If it goes past one pigeon, the other pigeon can eat, and if it goes the other way, the other pigeon eats. So that there is it's a real game. The pigeon is reinforced for a cross-court shot if that is what gets the ball past his opponent.
Okay, I'm going to stop it there. Okay, so what you can see in that video, well, it's certainly a game, a sort of ping pong game, no? In which these two pigeons are playing the game, and the task to learn is, well, when they pass the ball to the other side, if you see this small hole in the box, they are going to be getting food. So obviously, they are reinforced when they actually score points or put the ball on the other side, no? And this is linked with something which is called instrumental or operational conditioning, as say here. Or another way to say this is stimulus behavior learning. This was proposed by Tourniquet more than 100 years ago. And it's also linked to other approaches like classic conditioning, or also sometimes called Pavlovian conditioning. Have you heard about Pavlov's dog? Pavlov's dogs? Some of you. Yeah, okay. So for the ones who are not familiar with that experiment, quickly to say, that consisted of, well, a setup in which they wanted to, well, demonstrate that there are some links between certain stimulus, no? So for instance, the first part of the experiment consisted of giving some food to some dogs. And when doing that, Pavlov observed that the dogs, in that case, started to salivate, no? Because, well, previously to when they started before eating, they create more saliva, okay? Then, in a total different stimulus, a bell was ring, okay? So obviously nothing happened, no? There is no reason for making silent. But in a third stage, both stimulus were put together, no? So food plus bell ringing, no? So obviously the dog started to salivate again because of the food. But there was a connection, a link between the food and the other stimulus, no? So what observed Pavlov in those experiments is that after repeating that a few times, ringing the bell would create or would make that the dog start salivating. In other words, they created a connection, a link between these two separate stimulus, independent stimulus, no? Well, that is slightly different to this, to instrumental conditioning. Because in the classic conditioning or Pavlovian conditioning, basically the dogs were reacting to this stimulus, no? It was a reaction. But here, well, there is a reinforcement coming from something that is learned. So in here, the pigeons needed to learn something. It's not a reaction. They learn how to put the ball on the other side to get a reward. You know what's slightly different? And certainly, this idea of learning by interacting with the environment is not something new or something exclusively for machine learning, if you want. That is something that indeed happens in the brain, okay? There is an area in the brain which is able to, I'm gonna say like this at the moment, it's gonna able to understand or to link some state of happiness, which is actually reflected for higher levels of dopamine, a neurotransmitter. So when you do something and you are happy about it, this level of dopamine is going higher in the brain, okay? We are not going to review here how this works in the brain because it's not really related to this. But the point is, this is a bio-inspired approach, something that really, it does happen in the brain. And then we are going to take the same idea to build our reinforcement learning in the machine learning aspect, no? So here, in this approach, there is no explicit instructor. So it is possible to learn something when an agent is interacting by itself in the environment. Well, you may argue that, oh, but sometimes you need an instructor. Well, yes. For sometimes, well, that could actually speed up the learning process. Okay. Nevertheless, for most of the tasks, you don't really need an explicit instructor. You just need to have a connection with the sensory motor aspect. So you need to know how the environment answers to what you do. If you are able to do something and understand what happened around you, okay, so you actually can make a link, a connection from your actions to the state, okay? Well, now if we put this in a sort of robotics scenario, we can say that we may have an agent in a particular situation, or state S, which is able to perform an action into the environment, okay? So when you perform that action, when the agent performs this action in the environment, well, the current state is going to change. So from the environment, you may obtain a new state, but also, which is relevant for reinforcement learning, a reward signal, okay? So this reward signal is basically what we are going to be trying to maximize over time, okay? So far, so good? Or too quick? Okay, so let's think about the pole balancing problem. This is a classic control problem. It has been used in reinforcement learning for as a benchmark for many, many different research. So the problem is about this card, which has a pole on top. So the card can move to the left or right. And the task is that you need to balance the pole on top of the car. Okay, like pretty much like kids when you play with a pole, something like that, no? The card is going to move around x-axis, and there is a limit in both sides. Okay. You need to find a way to represent the state, also called observation, okay? So in that case, for the pole balancing, the problem is represented with 4 variables, okay? The position of the card, the x-axis, the velocity, so how is changing that position, the angle of the pole, okay, and how this angle is changing, called angular velocity, okay? This is the most common way to represent this problem. Well, you could include a different way, well, more variables or even fewer variables, depending how you want to model this problem, and we are going to come back to that in a few slides, okay? But for the moment, let's the most common way to represent the state in this problem is with these 4 variables, okay? So the question is, if the agent controlling this card is in a position, and is getting reward for keep the pole balance, and the pole is going to the left, well, my left. What would be the way to keep the pole balance? What action should be taken in order to keep the pole balance if the pole is going to the left? You can move the car. What direction? To the left as well, no? Trying to keep, well, and depending on the angular velocity, that could affect as well the speed that you are going to be moving that car to the left, no? Because this is slightly going to the, slightly going to the left. Maybe you don't need to push much. Quite the contrary, if it's going, well, the angle is it's higher and moving down quicker, maybe you need to push harder, no? So again, you can imagine yourself trying to balance the pole, no? So there are certain actions that you can take in order to keep the pole balance here, no? In order to keep doing the task. So the image there showed an agent controlling a cart, keeping the pole balance. Well, there are some terminate conditions. So, for instance, when you reach one of the border, to the left or to the right, or after the pole it's going below a particular angle. Okay, you don't really need to wait till the pole go to completely down. And as I said here, well, even if you think that the pole balancing is a really classic and trivial or easy problem, well, it could be not so. I mean, so for instance, for this rocket trying to land, you can see that, well, it's pretty much balanced, no? Well, obviously here there are other variables, no? I mean, the dimension is not only the x-axis, of course. Yeah, but still. Okay. Okay. The purpose is just to give you a quick idea, an introduction. Now we are going to go into the details. So I hope with this introduction you have a rough idea very rough idea about what reinforceable learning is. Okay? Means that you are going to have an agent able to perform actions in an environment, observe what happened with those actions, and receive a reward signal, which is going to be, well, saying or promoting to keep doing that action or not, depending on associated to the state. Okay? Okay, so let's see something more in detail. So I'm going to talk now about the 4 elements of reinforceable learning. First, and maybe also connected to the introduction. So reinforceable learning is to learn what to do. So we are going to be mapping situations, I mean a state from where the agent is, to actions. So that's why learning what to do. Okay? So the agent should be able, about the environment, we say here sense the environment or the state. But obviously you could think of different ways to sense the environment, no? One may think, okay, I'm going to use a microphone to listen. I'm going to use a camera to see, or a depth camera, or a LiDAR, or maybe a text input, whatever. There could be different ways to understand what is happening in the environment, okay? But when that is determined, well, the agent needs to decide what action to perform in order, and how the state is going to be affected by doing that, okay? And something interesting is these actions may affect not only the immediate reward, so something that I do today in other words, can have consequences a few steps ahead from now, okay? Well, the classic example there is playing chess. So maybe if you know how to play chess or you have heard about it, there are circumstances in which you have to take a decision now, perform an action, and then you know that you are going to win in maybe 5 or 6 movements from there on, you know? So the reward could come later for actions taken right now, okay? And a challenge here is, and we are going to talk with more details about it, it's exploration and exploitation. So possibly I'm going to leave that pending for when we go to more detail, okay? Okay, so as I said before, we have 4 different elements in reinforcement learning. The first one is the policy, okay? Well, policy is indeed quite relevant because informs or says to the agent what to do or how to act in a particular decision. Remember we said that reinforcement learning is about to learn how to act, no? We need to learn what to do, what action to take. Well, that information is going to be contained in the policy. The policy is going to say what is the best to do in what situation. Okay, so we are going to look for how to learn a good policy at the end of the day, okay? This is linked with the set of stimulus response rules or association from the bio-inspiration. And this can be stochastic. That means that we could have certain probability associated to it. So deterministic would be that I know certainly all the time what to do in what situation, and I know what is going to be the outcome, I'm going to say, after taking that action of following that policy. But as it can be stochastic, sometimes the decision what to do could be slightly different given a probability, okay? Okay, the reward function. Well, in this case, the reward function is going to define the aim of the reinforcement learning problem. If you remember our previous figure, we receive from the environment a new, after performing an action, we receive a new state and a reward signal, okay? That reward signal is determined using the reward function, okay? Therefore, it's going to map this perceived state, or eventually, or state action pairs, into a number. It's going to be a real number. Okay, this real number could be positive, could be negative. Okay. The goal of the reinforcement learning agent is to maximize the long-term reward. So you are not, well, you are not actually worried for the immediate reward only, but rather how much you are going to be collecting in the long term, okay? This corresponds to, well, pain and pleasure in biological system, and also can be stochastic, so there could be some probability associated with it, meaning that you are not going to have exactly the same reward sometimes for same situations, or after performing the same action, okay? The reward function is a key point because it's something that most of the time need to be defined by the reinforcement learning practitioners. Okay, so when you define a reinforcement learning task, part of that also involves to define what is going to be the reward function, because the reward function is associated to the aim of the reinforcement learning problem. So the reinforcement learning problem is going to, well, the reward function of the reinforcement learning problem, it's going to tell us what we want to do. okay? Now, as we have the reward function, which is associated with this immediate value, immediate reward, we also have the value function, okay? I told you before that something that we need to pay more attention is the long-term reward, no? Well, this is related to exactly this, the value function. This shows what is good in the long run, okay? And the reward in an immediate sense. But actually, what you want is to have a good value. If you are in a situation in which you can obtain a very high reward right now, okay? But from that situation onwards, a not so good value, and then you have here another situation in which the reward is sort of okay, but from there on, a good possible value, that is something that I would prefer to do, no? I always mention this maybe silly example, no? That imagine that you have a deadline assignment today. But imagine that last Wednesday, you could have gone to a party with your classmates or friends, whatever. Well, maybe you went to the party. You had really good time with them. You enjoyed. You received immediate reward. You were happy. Your levels of dopamine were high. But maybe the next day you were really tired, you had no really time to finish your assignment, and that actually affected your long-term reward, which is actually measured as the value function. So obviously, if you have that deadline, going to the party is a good reward, but not a good value, okay? So that's why we say here in biological systems, this corresponds to more refined judgments or for saying about the future from one state, okay? The thing is, the actions that the agent needs to perform should be chosen, taking into account the value, not the reward, not the immediate reward, okay? Because we want to maximize reward in the long term, okay? And for that, it's not something that we are going to need to define, but rather it's something that we are most of the time, well, there is an optimal value function, true, but regularly we are going to use an estimation of it. We are going to be estimating how good is to be in one state or state action pair, okay? Well, optionally, you also may have a model of the environment. The idea here is that you are going to imitate the environment behavior. You're going to use that model to predict the state and rewards obtained in advance. So you also can make some something is called imagination rollouts, okay? And well, even though we say here is still relatively new, I couldn't say that it's relatively new anymore, but I would say that is under study. I mean, maybe less study than other approaches, okay? Okay, let's talk now about exploration and exploitation. Okay, consider that you have a reinforcement learning agent which need to decide what action to do. You have different options. Let's say that I want to reach that chair or that table over there, okay? And from my current position, I could move left, move right, or maybe going down, okay? Okay, if I'm here, and I have this option of going back forward, left, right. And I would remember my task is to reach that table. What would be the best action to perform? Well, moving left, no? And getting closer. Okay. Well, what if I'm here now? Or here? Maybe forward, or still left? Not that clear anymore. Right? Well, this is if I know how to reach the table, or where the table is. But the thing is, well, it makes sense that most of the time the agent chooses what it thinks is the best action. Okay? So from all possible actions, the agent should select what it thinks is best. Now, possibly you should make a post about to think what is best. Because one thing is when I have learned something about the environment, so what I think is maybe what the agent thinks is maybe more certainly about what the real situation. But imagine that at the beginning, I have basically no information. I don't know if it's better moving left, right, forward, or backwards. I don't know. I may have basically random information, and then I need to perform one to see and observe. Okay? So that's what it thinks is something that we are going to come back, I guess. But in order to learn, but if you keep performing, if the agent keeps performing the best action always, there is no possibility to learn beyond what the information that is actually contained, well, initially, okay? So occasionally, the learning agent should prefer a different action, okay? And let's think this in a maybe daily life example as well. Imagine that after the lecture, you're gonna go home. Possibly you have different options to go home. No, even you can actually, maybe if you need to go to the tram, you can use the holder, or you can go maybe near to Roundhouse. You can choose whatever traffic light you want. You could actually take the tram or maybe take the bus if both works. I don't know. When you get off, still you are gonna maybe need to walk a few blocks from wherever you get off to your place. I'm pretty sure that most of the time you are gonna be doing the same, even though there are many different options. Okay. That is possibly because you determined at some point that that was the best option, the best action to perform. You decided, oh look, for whatever the reason, because it's the shortest or because you like it most that way, for whatever reason you want to put, you determine that that is the best to do. Okay? So most of the time, it's what you're going to be doing. Nevertheless, imagine that you always take the same path, or most of the time, but then in an alternative path, there is a great new grocery shop, whatever. Well, if you never try a new path, maybe you will never be able to see that there is something new there, no? But as long as you start to explore, you would be able to discover new things, no? Which you wouldn't if you all the time keep doing what you think is the best, no? Okay. I always say here that maybe you are too young for knowing the clutch. Okay, the clutch is, I think, from the 60s or 70s, a band which has this very famous song. I guess the song, maybe you know it. It's called Should I Stay or Should I Go Now? I hope you know. but anyway, the songs say, should I stay or should I go now? They repeat, should I stay or should I go now? If I go, there will be trouble, and if I stay, will be double. So this is precisely this. What we should do? Should I stay or should I go? Should I stay in the same path all the time? Should I keep doing what I think is the best? Or should I maybe increase the amount of time that actually discovering new paths? Because obviously the possibilities to reach home are endless, I guess. You could decide one day, okay, I'm gonna walk home. Well, maybe I'm gonna spend 2 hours or 3 hours walking. But it could be a possibility as well, no? So the point is, how much should I explore new alternatives? So what we say here is that the greedy action exploit the current knowledge. From what I know, the greedy action is to select the best one. Okay? The non-greedy action, therefore, explores. Okay? Exploitation maximizes the immediate reward, and exploration tries to make it in the long run. Okay? But there is indeed this conflict between exploration and exploitation. Okay? If you try to explore that much, it's hard in some point that to learn a policy. I mean, you're still going to be able to learn, but it's going to be harder to converge because you are going to be all the time choosing or jumping between solutions that are actually from the optimal, maybe. Okay? So, what do we do for a reinforcement learning agent? Okay, so what we do here is we are going to talk and define the action value as Q star of A. Okay? So this is the value, if you remember, the value function. It is the value associated to the possible actions. Okay? Now, we don't know the real action value, really, but we can estimate it, no? And we call this QT of A, okay? There are obviously different ways to estimate this, and then we are going to be, while progressing the lecture, we are going to be checking others. But the simple estimation is to average received rewards when action A has been selected KA times. Okay? So the simple estimation is, well, to consider all the rewards that were received and then divide it for the number of times that that reward was received. Okay? So the simple average. Okay? Now, when the action has not been chosen any time at all, we consider an arbitrary value. For instance, in this case, we are saying that Q2A, the estimation, could be 0. Could be a random value, okay? Or pretty much what you did for the neural network weights or parameters. You could have a initial parameter, initial weight, like pseudo randomly chosen, no? But when you are having more instances of the action being selected. So when this converts to infinite, we say that then our estimation converges to the real action value. So, in other words, the more we know, well, the closer we are from the real value, no? So we have a better estimation at the end. Is that clear? Good. Now, in that context, as we can have an action value estimation, what are the possibilities to select an action when I need to decide? Okay? Well, the easiest and the one that only exploit is the greedy method. Okay? So, that's the easiest or simplest way to choose an action. When you have the greedy method, from all possible actions, you are simply select the one with the highest estimated value. Okay, so you have considered that for an agent in a particular state, you may have different actions to choose, and you have an estimation for the action value for each of them. The one with the highest value, using the greedy method, would be the one that you will choose. Okay? Which is this. Okay? Now, we just said that in order to explore and therefore finding new different paths, we should sometimes perform not the best action, not the one with the highest value. No? The way to address this by this method, epsilon greedy, is one of the simplest ones as well, is by, well, using an epsilon parameter, and that parameter is associated to a probability of performing something else. So in simple words, epsilon greedy is a greedy method most of the time. Okay? So it's 1 minus epsilon times a greedy method. So most of the time I'm going to choose the best action value, or the action associated with the best value. But I'm going to use this small probability to randomly select any other action. Okay? So for instance, if my epsilon value is 0.1, that means that 10% of the time, instead of choosing the best action, I'm going to say, okay, give me any other, and I'm going to try that one and see what happens. Okay? So in this plot, you can see the behavior for 2,000 agents and with different epsilon values. So for instance, here, the average reward accumulated for these different agents using different epsilon values is shown here. So the one in green is epsilon equal to 0, so meaning that there is no exploration. So it's the greedy method. But what you can see there is that agent start collecting reward, but quickly got stuck in a local maximum in this case, okay? And the use of different epsilon values may affect this. So you can see here that when you have a epsilon 0.1, you can get a quicker convergence. When you have a lower one, even though it seems that the agent still is going to converge, that convergence is happening slower, okay? And here you can see, well, the percentage of times that the optimal action was selected. Now, even though epsilon greedy is one of the most used approach, maybe, there are alternatives, and one of those is softmax method, okay, for the softmax action selection method, okay? So the main advantage of this is this, no? That, well, even though epsilon greedy can easily manage exploration exploitation, the selection of any random action when you have to explore is equitable, no? It's the same. In other words, the worst action is going to be as likely as the second best. Okay, because you need to explore and you are going to get any random, and you don't know, as it's fully random, you don't know actually if that action is going to be as, or maybe similar to the best, or really, really bad action, okay? This alternative, softmax, what it does is create, well, use this, this temperature parameter, which is here. And what you are going to do there is you are going to have action selection probabilities for all possible actions, okay? So, for instance, imagine that you have, say, something like 4 different actions going up, down, left, right, okay? And imagine that the probability of the first one is going to be 0.5. This one is going to be 0.2, 0.15. No, let's make it, yeah, that doesn't matter really. Okay, we have 3 different probabilities there. Sorry, well, 3 different, but these 2 are equally bad, let's say. You can have here the cumulative probability. So this would be 0.5, this would be 0.7, 0.85, and 1. So now, if you draw a random number between 0 and 1, and imagine that the number is 0.6, what actions would you be taking? The second, correct. Now, if you can see here, the area, this is actually larger than this one, and this one. I mean, the coverage between 0 and 1. Therefore, when a softmax action selection method, the probability of selecting the best action is much higher. Still, a worse action can be selected, but that is going to be associated to the probability of that particular action from the particular probability action selection probability, okay? Now, this parameter, what it makes is that at the beginning, all probabilities are very similar. Therefore, I can take any. At the beginning, exploration is promoted. But over the learning episode, that temperature parameter is decreasing, and then the probabilities start to be slightly different and more different over time. Therefore, when I have the cumulative probability, the chance of getting the best one is going to be higher. Okay? Okay. Let me see the time. Okay. Is exploration and exploitation clear? Okay. Sorry, if we can call like together? Yeah. Well, you could combine. You could. Well, there are other actually ways to.
Like the A-star algorithm itself is a combination of UCS and the greedy algorithm. So one is exploration and one is exploitation. So can that be called?
Well, I think that depends how much you know about the environment, no? Because if you know, I mean, well, for instance, in a grid war, well, you could perform algorithms like A-star, and then you know what is going to be the best path, no? But then imagine that you have even a grid work with a lot of walls, and you don't know the walls, or you don't know maybe where they are, or obstacles to say. Well, in that case, well, you need to do the exploration, exploitation. Okay? Yeah. Any other question? Okay. Okay, let's talk now about the agent-environment interface. Well, there are indeed multiple reinforceable learning methods. So we say that any method able to solve a reinforceable learning problem is going to be a reinforceable learning method. Okay. The general framework or general reinforceable learning framework is the one that you can see now on screen. Okay. That is taken from the Satter and Bartow book. And it's pretty much the same I have shown with this robot figure before, no? It's the same because, well, here you have an agent which is in a particular state. From that state, the agent performs an action. And the environment answers with a new state and a reward signal, okay? Well, this bar here is showing that the new state become the current state after that to the agent, no? Well, here the agent set, it's going to comprise the learner and the one making the decisions. So there are two parts there. We say here they can be separated as well. And we are going to mention that later. When they are separated, they are called actor-critic approach. So you can have in the one side the learner, which is going to be learning the values, okay, the critic, and the one making the decision is going to be the actor, okay, the one saying, okay, what is the policy or action to perform, okay? On the other hand, the environment is everything external to the agent that the agent can interact with. But that which sounds very simple may also not be. One example for that is if you consider an agent learning to drive a car. Okay? So in some point you need to decide what is going to be the agent, what is going to be the environment, and what is going to be the border. Okay? And there could be different approach for exactly the same high-level problem, no? Because we just said driving a car. So maybe the easiest way to think this, and maybe the way that you also would think about is, well, yourself being the agent, no? Therefore, how you will controlling the car. Well, you say, okay, the actions are gonna be defined in terms of, well, the steering wheel or maybe the pedals, or going to direct, reverse, etc. Okay, the gearings. But yeah, that's an approach. But if you look to the other side, one different approach could be considering maybe the agent in a more wider way, in which the car itself could be part of the agents, and then you can see, oh, the turn of the wheels, maybe different angles. You know, so in that case, the agent would end where the car finished, or where the car touched the pavement, no? Or you can see this to the other side, no? You can think that, oh, maybe the agent is gonna be on a level of the human brain, and then you are gonna have your sensory input going, and the decision is gonna be motor skills, producing movement in the arms to control different aspects of the car. So what would be a good representation? Well, it depends, no? Depends what we want to solve. Okay? So that's why I'm saying that it may look trivial, and I guess for many cases you don't need to overthink about it, but sometimes could be different or could be complicated in the sense that a similar problem can have different level of abstractions. Okay? Okay, so if we look at the framework, some components that are present there, well, I think we mentioned most of this, but so I'm going to go quick in this. Well, the reward, we mentioned already that is a real number, okay? And the agent is going to try to maximize in the long term. We are going to have a set of possible states, okay? Maybe let's think at the beginning as discrete states, but actually this could be continuous as well. Okay. You are going to have actions available for each of those states. So actions that I can perform while facing a particular situation. And we are going to have this map from states to action, and this map is called policy. Remember? So the policy tells the agent what to do, no? So policy is represented by pi in this framework. So where the policy or pi of action given the state is the probability of taking action AT, given that the state is ST. Okay. So reinforcement learning method at the end is a way to learn, to learn the policy, no? In other words, how to update the policy as a result of the experience. So the experience here is we call this episodes, no? So the more experience, the more episode, the more times I updated the policy, means that the better I know what to do. Obviously, at the beginning, the reinforcement learning agent doesn't know anything about the environment, most of the time, and therefore, you are going to be sort of trying actions, observing what happened, trying again, observing what happened. But the more you do that, the more information you have, okay? And therefore, you can use that information for the coming actions to perform, or the policy. Okay, this simple example is about a recycling robot. We are going to come back later to a more detailed version of this, okay? So I'm going to read this. The agent decides if, so imagine that you have a robot that, it's going to be recycling cans, okay? So possibilities: 1, actively search for a can to recycle it. 2, remains stationary and waits for a can. 3, gets back to the home base to recharge or the docks. So you have here 3 possible actions: look for a can, or search for a can, wait for a can, or go to the dock to recharge, okay? So we could say here that the state for the reinforcement learning problem is going to be determined by the battery state. So we can see if we have enough battery or low battery, and therefore, given that observation, we are going to need to decide or make a decision what to do, okay? So in terms of the reward function, we are going to say that mostly 0, but it's going to be a positive reward when can is collected, and a negative reward, which should be much higher in comparison, when the battery is or runs empty, okay? So if the robot is not able to come back to the dock and recharge, that means that someone needs to go there manually, pick up the robot, and take it to the dock station or to recharge. Okay, so that's something that we want to highly penalize, okay? We don't want that intervention. So the action, in terms of keep searching, waiting for a can or going back to the dock to recharge, is going to be done based on the battery level, okay? How much energy I have. Is that clear, the problem definition? Where at the borders, we are going to come back later with more details about this example, okay? But in a high level, so far, is understood? Okay. Well, goals and reward, I think I already mentioned this. The agent goal is to maximize the amount of total reward over time, the long term, not immediate reward. So a few examples for the reward function. No? A robot learning to walk receives a reward proportional to the forward movements. No? So how much the robot was able to move in that direction, walking. A robot learning to escape from a maze receives a reward equal to 0 until escapes and then receives +1. So in that case, we have something that we call a sports reward, because most of the time the robot moving over the maze is gonna collect 0 reward, no value in that signal. But then when escape, +1. Okay. Another strategy for the same problem is to receive a reward equal to -1 after each movement till escaping, and then the reward is 0. So the difference here is, in the previous approach, I'm going to try to escape that maze. So I'm going to receive 0, 0, 0, 0 reward, 0 reward. When I escape, +1. In the other strategy, the second case, every step is going to be -1, -1, -1, -1, -1, -1, 0. Obviously, if I choose a longer path, the times as I receive -1 is going to keep accumulating, and therefore the total reward is going to be less. Okay. Here, an agent learning to play chess received +1 for winning and -1 for losing. Okay. Should you give some reward if you take an opponent piece? Why? Increases your chances of winning. Yeah, but but if you have,
Depends on what coin it is.
depending on what?
Coin it is. If it's a queen or a rook,
Well, it may also depends what piece. Yeah, sure, but.
and winning should have more points compared to taking over points.
Yeah, the thing is you need to think this. If you have the chance to win, you are going to receive a reward, no? But in that case, say +1. Okay. Remember that the goal is to maximize the reward in the long term. So, if you have the chance to take whatever piece, even the queen, okay? And I don't know, let's say that you are going to give me 0.5 just to encourage to take pieces, no? Because you want to say that there are more chances to win. Okay, if I win, I receive +1. And I have the chance to win now. Why should I win if I keep being in the game maximizing my reward? I'm going to take the queen +0.5, maybe another piece +0.5, maybe another piece +0. You know what I mean? So in that case, the agent actually could learn not what you want. The agent could learn to take more pieces, not winning. So you need to be very careful when you decide what to give reward to, okay? Because as we said next, the reward function should say what you want to achieve, not how to, okay? This is what we said here, no? Oh, sorry, wrong screen. This one, okay? Yeah, the agent may learn to maximize sub-goals. Because again, the goal is to maximize reward in the long term. Okay. In reinforcement learning, there are two different groups of tasks. They are called episodic and non-episodic, sometimes referred to the non-episodic referred as continual task. Not confused with continuous domains or continuous state actions. Okay, so that's why I prefer non-episodic. Well, I'm going to start explaining this problem. The mountain car task is also a very well-known reinforcement learning benchmark, which consists of this car, which need to reach the top of the hill at the right side, okay? But the car engine is not powerful enough in order to reach the top by simply accelerating, okay? Therefore, the way to reach the top to the right hill, it's by building momentum, like going forward, backward, and then at some point, you're going to be able to reach the hill to the right. That is a episodic task because it has, you can see, it has clearly a final state. The final state is to reach the top. When you reach the top, the task is finished. You can start a new learning episode if you want. Okay, but you achieve the task. In the other case, the pole balancing task, which we mentioned before, is a non-episodic task. In principle, I'm going to say there are variations anyway, but in principle, non-episodic task because it's a task that do not necessarily have a final state, but rather it's a task that you want to keep performing over time. The longer, the better, no? You want to keep the pole balance on top of the cart. Well, potentially to the infinite, no? Infinite time. Well, for many frame with our environments, there are ways still to make it sort of episodic, to say, okay, after a maximum number of episodes that you have been balancing the pole, I consider the task to be achieved, and you can make it anyway at the end of the day episodic, no? Say, okay, yes, it's done, it's done. I learn it, I consider learn, and don't need to keep going on. But it could be as well. But that's the difference between the episodic and non-episodic task. The episodic has a clear final state. The other one are tasks that you want to keep running over time. Now, why we are mentioning this? Because of the returns. Okay, so for every time step or for every episode, you are gonna have a reward signal. No? So after performing an action, remember the framework, you will receive a reward signal. No? Well, new state, reward signal. Therefore, you are gonna have a sequence of rewards. No? And we want to maximize something which is called the expected return. Well, actually, it should be the return here. Okay? The expected return is the value. We're going to go to that. Okay? So the return here, we can consider it like to say simply the addition of all rewards received in every time step or in every episode. Okay? When you have a final state or episodic task, well, you can easily divide this into sequences, or then you have one reward for each of them, no? An episode. So the episode finish in one of these final states, and then you can start another episode from the initial state. Sorry, wrong direction. Now, in non-episodic tasks, or the ones that are performed continuously all the time, well, the return, if we consider the previous equation, could be potentially infinite, no? Because you want to go as long as you can. So in this case, we use the discounted reward parameter, this one, gamma, okay, in this way. So every reward is multiplied by the discount factor or discount rate to the power of what time step it is, okay? So the discount factor determines the present value of future rewards, okay? Well, if this value is 0 near to 0, we said, well, the agent is myopic. If the discount factor is closer to 1, we say that the agent is foresighted, okay? Now, we also have for this a unified notation for considering episodic and non-episodic tasks. So basically, we use the same notation as for non-episodic, but we also add this absorbing final state with 0 reward for all coming possible actions after the final state in episodic task. So in that case, we say that, well, the number of steps could be infinite, or the discount could be equal to 1, but not both at the same time. Okay? Okay, so in the first case, consider the shown reward sequence, so 1, 0, 0, 0. The discount factor equals to 0.5. What will be the return? That is easy. 1. Because we obviously going to consider that. Second example, same discount factor. The reward sequence is 0, 0, 2, 0, 0, 0. What would be the return? Correct, 0.5. Well, you are going to be considering this one, no? So 0.5 to the power of 2 times 2. In the third case, exactly the same reward sequence as before, but the discount factor now is 0.9. How much would be? (0.9 to the power of 2). You said that, no? 62? That's correct. Well, the last one, we are not going to compute it here, but you got the idea. You can check it at home. It's 2. Okay? Okay. Just a second, since we need to make the break. Yeah, after this we make it. Okay. So let's talk about the Markov property. In reinforcement learning, the state is the information that the agent has available to make a decision, no? That's going to be determining what action to take. The state should inform everything about the environment to the agent. So, sorry, should not inform all the information to the environment, from the environment to the agent. So, for instance, an agent playing blackjack should not know the next card in the deck. Okay? So we do not blame the agent for not knowing something important if that hasn't been experienced, but rather we do blame the agent for knowing something and then forget it. If they experience something and then forget it, okay? Now, the best case scenario, the state should contain compact information about the past, retaining relevant information. So the Markov property says that all the information from the environment, all the information needed to make a decision is contained in that state. Okay? That is the ideal case. Well, very good example is the chessboard, because when you see the chessboard and need to play, it doesn't really matter the history. It doesn't really matter how you reach that distribution of pieces. It doesn't really matter what pieces were taken first or after, or how they moved before. That's all information you need to know that the next best movement is whatever, maybe move one, that pawn or whatever. Okay? Do you all understand that the chessboard contains clearly summary information to make the decision, no? Regardless the history? Okay. But again, this is the best case scenario, ideally. There are some times in which this property cannot really be fully satisfied, and there will be many cases indeed, okay? Still, reinforcement learning can deal and cope with many of those situations if the Markov property is achieved in some degree. No? We said before about the pole balancing that in order to make a good decision, we need to have information from 4 different variables. Remember the x position of the cart, the speed, well, velocity actually, the angle, the pole angle, and angular velocity. Well, but that is enough to make a good decision and what action to take. But indeed, you are not considering, if you put that into real life, there are gonna be things that you are not considering and for sure may affect the decision. No? Some examples here said some distortions, like, so for instance, delays, or even the temperature of the wheels. You know, if the wheels have higher temperature, they are going to move different if they are cold, no? If you like Formula One, you have seen this happening all the time, no? Like the temperature of the wheels is affecting the performance of the cars. And these distortions are not really considered in these 4 variables. Regardless, our reinforcement learning agent can deal with that quite well. And in some simplistic, I'm going to say, studies, the pole balancing has used observations like the one shown there, like dividing simply, instead of knowing the exact position of the car in the x-axis, just dividing the region in left, right, and center. And still working good, okay? So my point is here, the Markov property, it is achieved in certain way, no? Because you still have a summary information there in that state, even if you use left, right, and center, regardless the past. It doesn't really matter where the car was before. Now, that information is super specific, not necessarily, okay? But still could have Markov property there. Okay, so reinforcement learning task which has the Markov property, we call it a Markov decision process, so MDP, okay? MDP consists of these 4 different variables. The first one is S, finite set of states, A set of actions, delta, which is the transition function, which consider the state and an action. Move this and as the output is another state. So the inputs here, state and action, the output another state. And the reward function, which as input use the state and the action and gives a real number as the output, okay? Okay, so if we come back to the previous example that we announced in a sort of high level, the recycling robot now can be defined as an MDP, as a Markov decision process, okay? So we had said already that the robot could either actively search for a can or wait for someone to bring a can or get back to the home base to recharge. So we are defining here that the best strategy is to actively search for cans. So this should be affected in terms of the reward, no? in case of the battery runs out, something that we said before that we want to avoid, the robot needs to be rescued, leading to a negative reward. We also said before, much higher reward, much higher negative reward. The agent solely decides as a function of the energy level of the battery. We said that the observation or the state is going to be represented using the battery level, no? So here we are going to be defining simply two levels, high and low. So the battery could be either low battery or high battery. Okay. You may have more. I mean, certainly, as we just described before for the carpool, no? But here we can assume these two. So that represents the state. Possible decisions or agents' actions are, well, wait, search, or recharge, which are associated to these three that we mentioned before. So when the state is high, the available or possible action in that state are going to be search and wait, and when the battery is low, the actions available there are search, wait, and recharge. Okay? Sorry, before. The Markov decision process definition is something that, again, you, as a reinforcement learning practitioners, are going to have to define. You are going to have to say, okay, these are going to be the, well, unless you use an already defined environment, no? But if you want to define your own environment, you are going to need to define, okay, that's going to be my state representation. That's going to be the actions available for the state. This is going to be the reward function. And this is going to be the transitions. Okay, so the transition probabilities and expected reward are shown here in this table. So let's focus first in a couple of them, and then we extend to others. So for instance, I'm going to start with this one. This one here is showing a high negative reward. So what should have happened there? If you have such a high negative reward, what happened from the definition before?
Someone needs to pick the robot.
Exactly. So the robot ran out of battery, so someone had to go and rescue it. Okay? So if you see here and check this part, you can see that the current state was, before well, when that happened, no? The battery was low. And next state is battery high. How that could happen? Let me explain this in full. The battery was low, and I decided to do search, perform this action. And then the next state is high. How could that happen? Again, you're right, because someone had to go rescue the robot, put it to recharge, and obviously the next state is high because the robot is recharged with the battery recharged again. But that led to a high negative reward. Sometimes called punishment, but not anymore. I mean, probably former. Okay. So that led to a negative reward to get the battery high again. You can see maybe others, like, let's see this. We say here that if the battery is high and we decide to wait, the next action, having battery low, has a probability of 0, meaning that we are assuming here that the battery is not being consumed if you are basically doing nothing. Okay? Now, similarly here. That's the other way around, no? If we have currently a battery high and decide to wait, the probability of having a battery high is going to be 1. Okay. Here another one. If the current state is battery low and my action is going to recharge, the probability of having a high battery next is going to be 1. Okay? And for the same situation, having the battery low is going to be 0. Here. If the battery is high and I decided to search, the probability of having the battery high as a next state is a value of alpha. Okay? So the opposite situation, having the battery low, is going to be 1 minus alpha. Okay? We didn't stop before in the probability when the battery was low and decided to search. Okay, the results, because, well, I could decide, the robot could decide to search and remains with the battery low. Maybe it still had enough battery for doing that, but that's going to have a probability of beta in that case. Well, and so on. Something that we mentioned before is that the reward for search should be higher than reward for wait, because the best strategy was keep searching for cans instead of waiting or being stationary waiting for cans. Okay? The same can be shown graphically. In this case, well, the nodes here show the different states, and the transitions are shown. So, for instance, here you can have search when the battery is low, which could be, if you see, could go to high, but that meant that the robot need to be rescued as before, or with a probability of beta can keep having the battery low, therefore keep searching, and so on. This is exactly the same, but shown graphically instead of on a table. Good. We are going to make now a short break. We should talk later about value functions, temporal difference prediction, very quickly about other approaches as well. Okay, so we come back in 10 minutes, please. Okay, let's start with the second part. We have to talk now about value functions. So what did we say it was the value function? What do you remember we said it was the value function? Is there? Is the expected return. And what is expected return? Well, it's the long-term goal, no? It's what we want to maximize, no? So we also make this analogy with the more refining decisions from biological system, no? Refinement judgment that you can do, no? So think in the long-term or long-term decisions, okay? So instead of looking only to the immediate reward, like something positive, you want better, or rather to look as to maximize, the value over time. Think about it. Think about the value of a state value. How good is to be in a particular situations from now on. Okay, so maybe in this situation I'm not getting good reward, but I'm in a great place in order to accumulate reward in the future. Okay, so that's the value, so to speak. Okay, we said before that as well that to determine the value of function is indeed something more complex, but something that we are going to be doing here is basically working with value function estimations. Okay, so there are different methods to achieve that. A first division here is to consider that we could work at a state level or action state pairs, no? So we can estimate the state value function, as I said before, how good is to be in a state for the future, or we can also say the action value function, okay, which refers to state action pairs. So how good is to perform an action from this state for the future. Okay, so in the first case, how good is to be in this state? I still have all actions possibilities. The second one, how good is to be in this state and perform an action for the future. Okay, so that's why the second is considering state action pairs. Okay, so this is what I said before. No? The function estimates how good it is for the agent to be in a given state in terms of future reward or expected return. So the value of a state S under policy pi is denote, I actually writing down here both, the value of the state under policy pi, but sometimes you will see it using capital letters or something like a sub-index or on top. That could be shown differently, okay? But what you need to understand, that even maybe in this slide could be denoted different, but what you need to understand that the value functions denote, well, what is the value of from that state following that policy. Because the value is related with the policy. So as I said before, it's going to be how good is to be in that state for the future reward, but the future reward is going to be determined by the policy. The policy is the one mapping what action to perform, okay? So it's the value of, well, or the expected return when starting in the state S and following the policy pipe thereafter. So obviously the value, it's going to be the expected expected return from state S, or in other words, this is the return, as we said before. Okay, so the value of a terminal state, if any, for episodic task, is going to be 0, okay? The value of taking the action 8 in state S under policy pi, now this is the action value function. So we denoted this like Q, we use the letter Q for action values. Or, as before, we sometimes going to see this denoted like that. So similar as before, the Q value, which is the action value of the for the state and action, this state action part, is going to be the expected return when the state is ST and the action is AT. Okay. So this value functions can be estimated from experience. Therefore, as we said from the beginning, the agent needs to interact with the environment, observe, and get an experience in order to make a better estimation of the value functions. Okay? In principle, if the task is, well, I'm going to say small enough, okay, you could have a discrete representation. Okay? So for instance, you could have something that it's called Q table. Okay? The Q table is going to map these state and actions. To say, you can have here state 0, state 1, state n, whatever. Okay? And here you will have action 0, action 1, action m. This table could be used, the Q table could be used to store the Q values. Okay? So for instance, if in state 0 we have here a 0.9 value, 0.1 minus 0.3, whatever. Then the agent is in state 0. You could use the Q table to map the policy, no? So for instance, if you use a greedy action selection method and the agent is in state 0, what action should the agents or would the agent choose to perform in that case? With the greedy. Which one?
The greedy.
Which is?
Which is just chasing the near east.
We have 3 options there. This action 0. Because if you see here, this is the one getting to a higher, sorry, this is the one getting to a higher, sorry, showing a higher value. Okay, so this is the, again, remember that we said that before that the action should be chosen taking into account the values. And this is with the higher, this is the one with A0 is the one with the highest value. Therefore, in other words, is the best action or the action to choose in order to get good reward thereafter. Okay? But again, this is an estimation. So think about how we are going to populate that Q table initially. Well, it could be an arbitrary number, no? It could be to say simply all zeros. Well, obviously, if all zeros, that is not really correct, no? I mean, well, it's not what we want to achieve. It's not going to give us information to discriminate what action to choose in every situation or state. Well, it could be also randomly. But still, if random numbers are there, they are not really giving us information to decide what action to perform. But we should update this table, well, which is basically a function, from experience. So every time that I perform an action from one state, I'm going to be able to observe what is going to be the reward. And that's going to be information that I'm going to be using in order to update this table. And we're going to go to that in 1 second, okay? Now, sometimes you can have simply too many states or too many actions, or continuous state and actions, making impractical to keep these values or this Q table for every possible combination. Okay? But in that case, we can use parameterized function approximators such as well, if it's a linear problem, but but to approximate a nonlinear function, neural networks, for instance. We can use neural networks, indeed. So, if you think of what you can have now is going to be, for instance, a neural network in which the input is going to be, what's going to be the input? Well, the state. What is the situation? It's basically, imagine the table. And what is going to be the output? Well, could be different, but in this example, you can have maybe a M output, for instance, with Q values. You can have the Q values as output, no? Well, if you have, again, discrete actions, because you can have continuous state, discrete actions. So another possibility is, instead of having Q values here, is having directly policy here. To say, well, which could be, for instance, a probability distribution about a particular actions. Okay. Yeah, but this is something that you possibly are gonna explore further when you do the assignment. Okay. Because you are going to be using neural networks for that. Okay, the value function here. Well, we just said that the value is the expected return. So we could use this to compute it, no? I think I already mentioned this. I'm going to move. So it's said already, a value, yeah, it's the, yeah, well, the value of the state S following the polar with pi is denoted like that, no? So is this the value for in that state, but following this policy, okay? Now the maximum value or the optimal value is denoted with the start. That is what we want to have, no? We have an estimation, and this is what we want to have, the optimal or maximum value. Therefore, the maximum value is achieved by following the optimal policy. Well, in this case, we can make the simplification that actions are deterministic, meaning that every time that I perform an action, I know really what it's going to be the next state. But it's not always the case. That could also be not deterministic or stochastic. So imagine this example here. We have here in blue the immediate reward. So when if an agent, well, this is the goal position, what we want the agent to reach. In this very little grid work, imagine that the agent is going to be navigated, so going up, down, left, right. And the immediate reward, as you can see, is going to be 0 all the time, apart from these two situations. No? So in these cells, the agent could move to the right, and then it's going to receive a reward equal to 100. In this case, it's going to move, if the agent moves up, it's going to receive a reward equal to 100 as well, which is given by this goal. Well, what is in red is actually the value function there, or the values returned by the value function. So now if you see here, and here as well, the value is 100 because the value for that state following the optimal policy, so the best possible action, is 100. Obviously, you could say, oh, what if I go down? Well, yes, but that's not the optimal policy. If you follow the optimal policy, the value there is 100. Similar here, no? Here and here. If you follow the optimal policy, and then obviously remember that you need to use the discount factor, in this case 0.9, therefore the value in those two cells is going to be 90, following the optimal policy, and in this case 81, because you are going to be using this, the second term. Well, you can also relate the value function with the Q value, or the action value. So you can say that the action value, it's going to be the immediate reward plus the discount factor times the value function. Remember that in this case we work with state action pairs. And this is showing, well, similar as before, this is the immediate reward. So I think I mentioned we have 100 here and there. These are the values that we can compute using the returns. And now, if we want to compute the action values, the action value is not going to be associated with the state, but rather with the possible actions taken from every state. No? So if the agent is actually here, the value of performing going to the right is going to be 100, well, which is actually the best. But from there, the agent could choose going, for instance, down, in which the value, the action value, is different because it's going to a cell in which the value is 90. Okay? Similar is actually deciding to come back. And here is 72, same as here, because it's going to a cell in which the value is 81. So the previous is summarized with this short video in which you can see the red arrows show the action value. No? So what you can see that the actions are computed while the agent is collecting experience. I'm gonna start over. Okay, so at the beginning, well, you know that the agent is going to start exploring. In some point, trying these different possible actions is going to reach the goal. And that is going to update that immediate action value. No? So if you see, oh, sorry, my bad. I'm going to play here. Then, when that happens, that action value is updated. Because I know, or we know, that the agent collected a reward there, no? But then, if we start over, that is not affecting, but then in some point, then that action led to a state in which the maximum action value was 100. So I can update this because I have already information from this state. And then when I start moving, I can update this then. And therefore, the other ones. Okay? So the point here is that the values are determined from experience. Okay? I think this is completed now. Okay. This is another grid work example. So I'm gonna read this information. So in this case, the state corresponds to the cell or cell position. 4 possible actions, let's say going up, down, left, right, or north, south, west, east. Actions leading the agent out of the environment do not change the position, but give a reward equal to -1. So let's say that is a, I don't know, you can imagine this as sort of table, which is surrounded by a wall, so you cannot actually fall down. You simply hit the wall, so remain in the same position, but that gives a negative reward of -1, hitting the wall. All other actions give a reward of 0, except when you reach position A or B, as shown here. Okay? If you reach A, the agents jump to A prima, giving a +10 of reward. If you reach B, you reach here to B prima, and giving +5 of reward. Okay? Okay, so what else? All actions have equal probability. The discount factor in this example is 0.9. And you can see these negative values near the lower edge. The best state is A, this is the one given +10, but the expected return is lower than 10, the immediate reward. And B is actually value more than 5, the immediate reward. So the question is why? Well, you need to consider that the agent here, apart from receiving the immediate reward, is also making a jump in the grid world, no? And if you go to this position, well, the agent is going to be closer to the end of the grid world, no? Or closer to a wall if you want. Okay? So there are chances as well of hitting the wall. That, well, if you see, so for instance, this value and this are the worst, no? Because you are actually near to this corner, well, you have actually a wall in 2 different directions, so it's likely that you can hit the wall receiving -1. You may think, oh, why here is not the case? Well, it's somehow the same case. Because, well, if you see from the first row, those 2 are the worst values. Still, you are in the positive side because they are also near from another cell which is giving +10 or +5. Certainly, you can hit the wall, but you can also get +10 or +5. still the words in that row, no? So yeah, when you make this jump, okay, you get plus 10, but you are positioning the agent very near or just next to the wall, no? While when you are moving to this position, we could say that it's a safer position, so to speak, no? In the middle of the board. So, well, this is the optimal values which are achieved following the optimal policy. Okay, let's jump now to the temporal difference prediction. Well, the method that we reviewed before, it's, well, a Monte Carlo-like method. But another approach called temporal difference is actually central in, I'm going to say nowadays, reinforcement learning, particularly in value-based methods. And what happened, well, the methods that we have seen before, they can update the value when you reach the end of the episode, because at that point you really know what is the return, okay? So if you need to wait till you can compute the return, okay? While temporal difference, what it does is, well, make an estimation of that, okay? So to say, they say, okay, look, we are gonna compute the value using an estimation of the value at the next state. So they are going to estimate the value at time t using an estimation, another estimation, of the value in the next state. So they use an estimation to perform another estimation. Okay. By the way, here alpha is similar to like the step size or learning rate in neural networks, just making like a smaller or bigger step for that game. So, well, this is the simplest TD learning method, which is called TD0. There are some variations that, well, I'm not going to be covered here. But what we are going to talk here is about two different approximations that can be on policy or off policy. So these are two related here. We are going to be related here with two classic methods. One of them is called Q-learning. The other one is called SARSA. And you are going to be also coding these two methods, both Q-learning and SARSA, in the tutorial. For a tabular problem anyway, a grid word, a small grid word. Okay. In TD control, we learn action value function instead of state value function. Therefore, we are going to consider here state action pairs. So we estimate the Q values for state actions while considering the current policy pi. Well, the first method that we review is called SARS, okay? That is called on policy temporal difference control. So in this case, the Q values are going to be updated after each transition from a non-terminal state. We have mentioned before, but if a terminal state, the value function is actually 0. Okay. So the way to update, so you can imagine again this Q table that I drew before, no? In which you have the state going down and the different actions. So imagine that now you want to update the Q values that are within that Q table. Okay. So after performing an action from one state, you are going to be able to update that particular Q value. Okay? And for that particular Q value, you are going to be updated considering the current value, well, the alpha or learning rate, the received reward, the discount factor, and here you are going to be considering the Q value of the next state, the one that you reach after performing the action, the selected action, and one next state. I'm going to come back to that one. Okay? Well, the method is simply called SARSA because consider these 5 elements, the current state, current action, reward, next state, and next action. In this case, the next action, or the action to be considered from the next state, is the one following the same policy. Okay? So the same action selection method. Okay? That's why it's called policy. So this estimation is going to be affecting here, no? So for instance, let's see the algorithm for this. First, we need to initialize the Q values with an arbitrary value, no? We said before it could be 0, could be random, etc. Okay? But we know that terminal state also are going to be 0. So we need to repeat this. We need to select initial state, where we are going to start, and choose an action from that state using a policy. For instance, epsilon greedy. So in that case, most of the time the best, sometimes I explore a different one. And we are going to repeat for each step of the episode. We are going to take the action that we choose before. We are going to observe the reward and the next state. We are going to choose a next action from the next state. Remember, this next action here uses exactly the same policy as before. And with that, we are going to update the Q table. Well, one element of the Q table, that Q value. Okay? Then we simply need to say, well, the next state becomes the current state, and the next action becomes the current action. So that's why the choose action from S doesn't need to be inside the loop, no? Because it's updated with the one chosen there. I'm sorry. Okay. Well, different method to update the Q values is Q learning, which is an off-policy method. Well, here, there are indeed a lot of variation from initial Q learning, no? But this is the original version. In this case, it's similar as SARSA in the sense that we are going to update the Q value considering the current Q value, learning rate, the received reward, learning discount factor, but the main difference comes here, obviously. Before, if you look at the equation, we said that we are going to be using the Q value for the next state and next action. But here, we are going to assume the optimal policy. In other words, at the next state, we are not going to choose an action using the same policy. We are going to choose an action or the best known action at the moment. That's why we are choosing here the maximum Q value in the next state. So in other words, we are going to choose the best action from the next state. In other words, we are going to choose that, assuming that the best policy is known there. Obviously, at the beginning, it's not, but it's going to be updated over time. So in this case, we said, well, the learn action value function Q directly approximate Q star, the optimal Q value. So here we don't need to use the current following policy, but rather assume the best action. Well, the algorithm for this is similar to SARSA in the sense that we need to, well, initialize the Q value, similar as before. We need to, we are going to give 0 for the terminal state. We are going to select a initial state, okay? And then we are going to repeat this, which is, well, we are going to choose an action from state S using our policy. We are going to take the action A and observe reward and next state, and then we update the Q value. Now here we only update the next state because the next action is going to need to be chosen from that state, okay? Before we selected one before, because, well, we use it for overestimation, no? But here, not really. So that's why here the action selection is inside the loop. Now, imagine this grid word, which is shown in the image. This one is from Sutherland Barton book as well. It's called the cliff walking scenario, or the cliff walking problem. So imagine that you have a learning agent starting from S position, bottom left, and the task is to reach the goal position to bottom right, okay? So as I said there, well, there is a reward of -1 for all transitions. So every time the agent moves, receive a negative reward of -1, except in the cliff. So if the agent step into the cliff, a much higher negative reward of -100 is given, and that also terminates the learning episode and send the agent back to the initial position, okay? So what you can see there is that there are, well, 2 possible paths. The optimal path or shortest path, which is just going next to the cliff, but you also could think it's a risky path, no? Because you are really going next to a very high negative reward, okay, the -100. And the other one is the safe path, but that is a longer path. Okay, so what you can see here is the reward per episode when using 2 different learning agents, one with using SARSA, and another one using Q-learning, okay? Now, interestingly, when we used epsilon greedy action selection with epsilon equal to 0, 1, well, the Q-learning agent is the one which learned the optimal path, the shortest one. And SARSA learned the longest path. But if you look again to the reward per episode, the one accumulating more reward is the SARSA agent, okay, for these parameters. Well, why is that? Yeah, because the key learning agent has 10% chance of stepping into the cliff while transiting the optimal path, no? Given the epsilon parameter equal to 0.1, no? 0.1. So obviously, if you modify epsilon, you are going to be modifying that probability. That's why we say, well, reducing that value, it's going to make both methods to converge to similar reward, no? Because the probability of stepping into the cliff is going to be lower, therefore, that's going to affect the total reward. So the point here is, it is actually not clear what method is really going to work. Is going to work better in advance. This, as many of the machine learning approach, they are highly linked with the hyperparameters as well. And you can see how that could affect. And that is just one parameter, no? But obviously, more or newer approaches, they may consider even more parameters or strategies to choose parameters or to modify parameters, because in that case, for instance, the epsilon value remains fixed during the learning. But nowadays, a more common strategy is to have a decaying epsilon value. Means that at the beginning you are going to allow a high value. In other words, meaning that you are going to encourage more exploration at the beginning. You allow the agent to perform any random action. But while you are moving towards over the episodes, that you start to decrease this epsilon value, and then after some episode goes, the rate of exploration becomes lower. Okay. Well, is that clear? So, before moving on, because this is the last slide from, I need to add another section here, I guess. Is temporal difference learning clear? That you can use it for estimate the value function? Well, you will anyway run a lab in these two methods, SARSA and Q-learning. So if not totally clear now, I hope it's gonna be totally clear after the tutorial. It's actually the algorithm that you have seen, that's all. It's very short code. So you are gonna be doing the SARSA and Q-learning method in a small grid world. And then you are gonna use another gymnasium environment called Frozen Lake as well. It's also a grid world, small grid world, to work with, with a different library as well. Okay. So now I just want to mention a few other possibilities to say, okay? Well, reinforcement learning is actually a huge topic, okay? It's hard to cover all that we wish in one lecture. Could be easily be a whole course, okay? This is pretty much an introduction, but still I want to mention at least a few other things that could be useful to take into account. Some of those as well gonna be useful when you work in your assignment, okay? As we mentioned in the first lecture, because someone asked, and I think was the right question to ask, I expect you guys in the assignments go further, okay? So for me, it's pointless if I give you an assignment saying, okay, resolve this with Q-learning. You are going to be doing that in the tutorial, okay? So it is expected that you study a few other things by yourself. Well, with our support, you can ask, but that's why you have the forums. But it's the way that we can also cover a bit more other things, okay? Okay, other thing that I want to mention here is, this is what we say here, a non-exhaustive taxonomy of reinforcement learning algorithms. Well, we have been exploring basically things that we call model-free reinforcement learning from what you have seen today, which is and even inside that, I'm going to say that we have been moving here in Q-learning, or value-based method. So we, in this method, estimate the value, and from the value, they can actually infer or derivate the policy, which is what we need at the end. Remember that the policy is what tells the agent how to act, mapping the state into actions. But now, we also mentioned there are some cases in which a table is not going to be linear necessarily, and this is, well, the most common problem nowadays. Tables are rarely used, because obviously we want reinforcement learning to work in real-world scenarios, and that means well, a bit higher complexity, continuous scenarios, and so on. No? So another way is, well, instead of learning or estimating the value function, you can also try to learn directly the policy, okay? So in that case, you are going to need to observe the policy after performing actions. And then the common method is use a gradient as well. Well, in that case, gradient ascent, you want to maximize, okay? I'm going to say that most applications nowadays move in this area of reinforcement learning, which is the one from model-free. There are indeed a lot of research nowadays in model-based and very good proposals, particularly things like work models. But here, well, some methods, I'm going to show a slide about it, is, for instance, deep Q network. Okay, deep Q network is, well, it's a network that was introduced, maybe a reinforcement learning with what method it was introduced maybe 10 years ago, I think, 2015, maybe a bit more. So particularly in that method, well, our neural network works with images in order to determine the values, or to estimate the values at the output of the network. Okay, I'm going to show you a few more details about it. There are other methods which use, well, gradients, as I said before, like TRPO, like Trust Region Policy Optimization, and a simplification of that, which also better results, is PPO. Also going to show a slide about it. You will be using that in the assignment. And there are some sort of mixed method, no? Like the DPG, TD3, or SAC, which can combine both approaches, like value-based and policy iteration. So this image is taken from the OpenAI Spinning Up library. There are indeed both methods, no? That's why I said non-exhaustive. So the Deep Q network, one of the ones shown before, was proposed indeed in 2015. This paper was shown in Atari games. So they claim that they got human-level control for different, I can't remember how many, could be like 40-ish different Atari games, or 20-ish, can't remember. sorry, here, 49. 49 different Atari games, okay? Do you know Atari games? The old Nintendo Switch, I guess. like the games in the 80s, no? Like Pac-Man or things like that, no? So you control with this joystick, which was basically the direction and one button, okay? They use an artificial neural network to estimate the values. So here what you had was the values and the output. The values of performing this action of going up, going right, up right, and so on. Or maybe up plus the bottom, and so on. Okay? So the values were estimated there, no? So as input, they use the image, where images were coming directly from the games. Okay, so you can see like a frame from this, and that was used to fit the network. Okay. So here at the beginning, you have a couple of convolutional layers in order to learn the features, and then you have a fully connected approach in order to determine the value, no? The value function. Well, a couple of additional features that were added in this method were the additional target network, because here the parameters of the network, of the neural network, were all the time change, because, well, and then the goal as well. That could create some instability during the learning, and also there is another problem which is called overestimation, okay? So this, with this additional target network, what it does is to create a copy of the network, and that is not modified for a number of time steps. So that remains fixed, and well, again, another parameter to select, no? But after some iterations, that is updated or create another copy from the original neural network, okay? That is basically to avoid this instability. And additionally, you have a memory buffer for experience replay, meaning that, experiences considering state, action, reward, next state, are going to be put in this buffer, and an experience replay is going to be performed. The network is going to be trained for using the information contained in that buffer. Okay? So instead of updating the network weights every single time step, you are going to, every time that you make a change, so to speak, from the state to another one, you are going to use the information in that buffer. Okay? Okay, another approaches considered were actor-critic methods. I mentioned at the beginning that the agent, when we described the agent environment framework, we said that the agent contains the learner, remember? We said, actually, we linked that with the value, and the one acting, performing actions, or deciding, or the decision maker, if you want, the learner and the decision maker. But there are many current new approaches which actually divide this into two. So now instead, you may have the agent, like here, no? So one part of the agent is going to be in charge of learning. It's going to work with the reward, no? So it's going to be estimating the value function. So it's going to be determining how good it is to be in one state. And another part is going to learn the policy, what action to perform then. Okay? So you can divide that in the actor and critic. Okay? One of the advantages, a couple of advantages. One of them is that, well, you need minimal computation to select actions, because, well, the load here is basically to learn the value function. And also, well, this seems to be more bio-inspired because it's appealing with psychological, biological models. It's more or less the way that our brain works. Okay. Another algorithm, which is in the side of policy iteration, if you remember the taxonomy, is PPO, proximal policy optimization. This is an improvement from TRPO. This is on policy learning as well. So here we have actor critic as well, so the actor to choose action and the critic to estimate expected return of the value. And the main contribution in this approach is that the objective function, which is called L here, use a radio between the new and the old policy, is this one, the radio, okay. Also an estimated advantage is here, and a creepy parameter. So the radio between the new and old policy is going to reflect how much the policy change, okay? But in this case, the objective function here use a clip value, which is between, well, it consider the radio value, but also 1 minus epsilon or 1 plus epsilon. A usual value for epsilon here is, for instance, 0.2. Okay, so meaning that the radio should not be beyond 0.8 and 1.2. Okay, so any variation beyond that is clip. If it is between those values, remains. Okay. Yeah, that is also that's also done to avoid instability. Because if you vary the policy a lot, that could create instability. So the clip function, what it does is that the policy is going to be, the next policy is going to be, in simple words, not so far from where we are. That's why it's called proximal policy optimization. The implementation of this is indeed a simple one. And given this clip function, you have a stable training as well. Nevertheless, could be as well less sample efficient if you compare with other algorithms like soft after critic, for instance. As I said here, there is an additional reading which I put in the additional material on Moodle. So there is a link to that paper from Schulman from 2017. So these people is from OpenAI as well. There is also there another link, which is not mentioned here, but if you really want to go beyond, the paper from TRPO is also from Schulman, and it's also there. So I think it's like 2 years older than that, okay? And if you want to go beyond, you should go to the reinforced paper, which is from the 90s, no? But I think that should be all right with that one. Well, remember that is your homework, please. Read it. You will need it. Okay. Okay, this is a old robot which was actually built here at CSE. It's called Stampy. You can see a Stampy in K70 level 1. This is still there, being shown under a window, no? Well, even then, like in the 90s, with not so modern reinforcement learning methods, well, this robot was trying to learn how to walk, okay? So in this case, the robot Stampy received a reward after if action, like, well, considering if the robot moved forward or not, okay? what you are seeing what you are seeing there is the robot performing actions before learning. That's why if you were thinking that, oh, that is not really working, you're right. Well, just after 30 minutes, again, in a very old-fashioned way, you can see that the robot now is showing a behavior, well, related to what we want to achieve, no? That the robot can move. Well, another example in this, well, this is not that old. It's done with using the Pepper robot. So in this case, the Pepper robot need to play that game, which is basically to put the ball on top of that cup. But, well, you also have seen maybe that in the first scene, someone was showing how to do it. So like using a demonstration. But thereafter, the robot starts to repeat that demonstration unsuccessfully for many trials. So after 70 trials, yes, you can see that the robot, well, start to get a bit closer, at least touching the cup, not yet done though. So after 100 trials, the robot learned how to play the game. Now, they tested the trajectory, the learn trajectory. So what you can see here is one attempt to repeat the task. And another attempt, and so on. Actually, there are 10 attempts. Well, to make it simple, the 10 attempts is actually successful, okay? Well, I think this is for today. Something that you also gonna find in the in Moodle is the link for this book, which is the Sutton and Barrow book. Is a must to read if you wanna go forward in reinforcement learning. The link is actually showing. Well, you can get the full book in PDF for free. There are code as well, slides, there are many things, okay? So I think it's, again, if you want to go into reinforcement learning, it's something that you should consider to read. Again, this is a very, I don't know, non-comprehensive introduction. What we have is, talked here. For more details, the book, I think, is something really needed. Well, thank you very much for coming Friday, for coming the deadline day. I'm sorry if something was not explained so clear. I have to say that I don't feel so well today. But if there is any question, please use the forum as usual or reach me. Because, for two reasons. You are going to be next week doing the discussions. And the tutorial about this is coming the week after. So hopefully you are not too disconnected from the lecture concepts or materials and then the practical one, okay? And again, you are going to need both the theory material and the practical one for your assignment, which we expect to open next week, okay? The second assignment about reinforcement learning. So thank you very much, guys. Enjoy the weekend. Please. I also like the hard copy, so I bring out. Let me a second. If we can make it short though, that would be really appreciated to be honest. But let me give me a second.
Excuse me, sir. I have some question. It's about the temperature. I see that some large language model also have the temperature. So if the temperature is low, what it means?
Yeah, no, that I can tell you, but in this context, remember that obviously in other contexts could be something else. For instance, I can tell you there is an optimization method which is called simulated annealing. They also use a temperature parameter. My point is, what it means here is not necessarily what it means in something else. What it means here means that when you have a high temperature value, if you look at this, well, this is using the exponential function, okay?
Yeah.
So maybe put whatever value, put some values just to play with it, and let's say 0.5, whatever, and then use a high temperature, for instance 0.9.
Yeah.
What you will see is that the final probabilities are going to be all more or less similar. A high temperature is going to be less difference between the final probabilities, while a lower temperature is going to make more difference between the probabilities.
Oh, so if we use the high temperature, so it's hard for us to it's hard for us to avoid the bad case.
Exactly, but a high temperature, in other words, means that it's basically you are going to be exploring more.
Yeah.
You're going to be doing more exploration.
It's more randomly.
Correct. That's correct.
And that's I also want to ask about this one.
Mm-hmm.
If this gamma be near to 1, it means that the result of it is not a convert.
Well, it could be near 1, but cannot be 1.
If it is 1, and the result can be a very large. So
Yeah, but imagine that you have 0.9 or 0.99. As you move towards, and this is going to be going a small number because the power of, you know. But if you have a number, if you have 1, you're right. That's going to be very large and potentially infinite.
Yeah. If it is 1, it will be good like this.
Yeah, that's when we say could be 0, but
Could be 0.
less than 1.
Yeah. And the last question, sir, I also want to ask about